Welcome back, everyone, to this session. It's my pleasure to introduce Chad Nestor from the University of Tallinn that will talk about situated transition systems. By the way, I will tell you when you have 5 minutes left, including questions.
Sure, thank you. So yes, as you say, my name is Chad. I'm a PhD student at Tallinn University of Technology, which it turns out is different than the University of Tallinn. That's another university. And I'm going to talk to you about what I've been calling situated transition systems. But before I do, I should mention that I'm supervised by Pawel Sobocinski here. So what I mean by a situated transition system is an open transition system that generates material history as it executes transitions in a coherent way. So that doesn't make a lot of sense right now. So what I'm going to do in my talk is tell you what I mean by open transition system, then what I mean by material history, and then say a few words about how to combine the two and what happens when you do. And by a transition system or an open transition system with boundary, I mean a span of reflexive graphs. So a reflexive graph is sort of a directed graph, directed pseudograph, quiver, if you like, where every vertex has to have a sort of trivial edge, like an identity morphism for a category from that vertex to itself. And how are we going to interpret spans of reflexive graphs as transition systems with boundary? Well, we think of these, so here's our prototypical span in the middle here, and we think of its feet, these graphs U and V, as these are the boundaries. And in particular, we think of their edges as telling us which events can happen. So the edges of boundary graphs like U and V, these corresponds to events that might happen along that boundary. And the apex of the span R is sort of the transition system itself, the meat of the thing, where the vertices of R are the states of our transition system, and the edges of R are its possible transitions. And then what the legs of the span do is tell us sort of what happens along the boundary when a transition happens. So they map transitions T, say in R, to some event that happens when T happens in R along boundary U, and some event that happens along boundary V. And because these are spans, I can compose them. And when I consider the composite as a transition system, I get that it's considering the two systems that I've composed, sort of they can do everything that they could do normally so long as they're consistent along the shared boundary. So if I compose R and S here on the right, then in the pullback, sort of what this being the pullback means is that the composite transition system contains, its transitions are pairs of transitions in R and transitions in S whose behavior along this shared boundary agrees. And that's how you compose these. And also this is a monoidal category because again, it's a category of spans. And the tensor product is sort of taken by taking the Cartesian product in reflexive graphs of just all the relevant data pictured here below on the left. And this is kind of having its independent systems considered both at the same time. So in S tensor R, anything that could happen in R and anything that could happen in S could happen sort of independently of one another. And where this can happen sort of asynchronously because I've included these trivial edges, I mean, my graphs are reflexive. So let's do an example. If I take, for example, my boundary to be this graph M, where there's one vertex and the two possible boundary events are called up and down, which we're going to think of as teeth of a gear moving up and down from the perspective of that boundary. And then I'm going to define an open transition system called gear from M to M as follows, and I'll explain this diagram. So M, each boundary graph is M. These are the feet of my span. The apex of my span I've put in the middle. This is the graph with one vertex and two edges, so one state and two transitions, one called CW, indicating that my gear rotates clockwise, and one called CCW, indicating that my gear rotates counterclockwise. I've indicated the legs of the span using colors. In particular, you see that if my gear rotates clockwise, then the teeth on the left will appear to move up, and the teeth on the right will appear to move down, just like if it were a gear. And if my gear, if my gear rotates counterclockwise, then the teeth on the left will appear to move down and the teeth on the right will appear to move up. And then I can compose these. So I can put my two gears next to each other, compose them along their shared boundary, which is just M. And in the composite system, if I compute what that pullback is, then I get that, well, of course, it has M as its boundaries again. And it has two transitions again, one in which the gear on the left rotates clockwise and the gear on the right rotates counterclockwise. They can't both rotate clockwise because they must agree on the shared boundary, in which case the teeth on both sides rotate up and vice versa, counterclockwise and clockwise, and the teeth go down. And then this is this sort of gear teeth synchronization is a good way to think about how composing these transition systems works. To sort of set up a later example, maybe we could consider a couple of open transition systems, one called Baker and one called Eder, where the Baker has two states. It can either be open or closed and can freely open and close, neither of which has any non-trivial boundary effect. The lack of color says that that has a trivial boundary effect. And if it's open, it can bake and sell bread, where if it bakes bread, this event X happens along the left boundary, and if it sells bread, this event Y happens along the right boundary. Then over here, we have eater. Eater can be hungry or full, and it can freely eat and digest to move between these two states with no effect on the boundary. And if it's hungry, it can buy bread, which sort of corresponds to this event Y happening on the left boundary. And so if we compose these, this is small enough that we can compute the composite, and there are all these edges, and in some of them, the baker bakes bread, and in some of them, the eater eats and digests, and I haven't labeled the ones with no effect. And the important thing to notice is that this sell and buy, these two yellow transitions, these have sort of become the same thing, trade. So in the state where the baker is open and the eater is hungry, they can sell and buy, and sort of this must be synchronized because they correspond to the same event along the shared boundary. So I hope this makes some sort of sense. And this is the sort of open transition system that I'm talking about. So now, what do I mean by material history? And what I mean by material history is I'm going to phrase in terms of resource theories, which are just symmetric monoidal categories, thought of in a certain way. So for example, I might construct a symmetric monoidal category freely with atomic objects, say bread, dough, flour, and oven, representing my basic resources, and generating morphisms allowing me to knead flour into dough, to bake dough into bread in an oven, getting the oven back as well, it's important, and maybe to eat bread, just getting rid of it. And then in the free strict symmetric monoidal category generated by this information, I can express composite resource transformations, which are sort of like slices of material history describing what has happened to these things. So for example, here, this string diagram expresses the sequence of events where this dough and this dough have been baked one after another in the same oven to get to bread and an oven. And the way, another thing, an important sort of observation, I guess, is that the way you really want to read these string diagrams, and in particular their equality, is that two string diagrams should denote the same morphism in case the sequences of events they depict would have the same effect on those resources. So, for example, in my bread theory, I could add a generating morphism sift that turns flour into flour, in which case I would want it to be the case that sifting flour twice is the same as sifting flour once, because that's kind of true. And so, to have that in my resulting monoidal category, I might need an equation like this. And this is how we're going to understand equality of string diagrams. Like the thing to note being that these are different sequences of events, because here sifting has happened twice, and here it's happened once. And this isn't quite enough. So if that's our material history, that doesn't have quite enough structure for us to use to give our open transition systems material history in the way that I would like to. We're going to need to make it into a single object double category. So to briefly recap, a single object double category has horizontal and vertical edge monoids instead of categories. So this is the horizontal one where A and B are drawn from, and of course cells, alpha. And so cells are bounded by a horizontal edge monoid element on the top and bottom, and a vertical edge monoid element on the left and right, and I can compose them vertically and horizontally to get more cells. And we're going to build a double category like this from our resource theory A, our sort of material history thing. The horizontal edge monoid is going to be the objects of A, and we're going to sort of put all the morphisms of A into our double category in a coherent way, just sort of like this. These are the coherence conditions. The main thing is that if I have a morphism in A, a transformation of resources, also that's a cell in my double category with trivial left and right boundary. And our vertical edge monoid is going to be the monoid of exchanges, which is sort of polarized sequences of objects of A. So for example, if A, B, and C are objects of A, then this would be an element of the monoid of exchanges. Sort of A circle tensor B bullet tensor C bullet where what I understand that to mean is that the exchange has a left participant and a right participant, and to sort of do this exchange, well, Alice, the left participant, would have to give Bob, the right participant, an instance of A, then Bob would give Alice an instance of B, and then Bob would give Alice an instance of C. So the white dot's going to indicate movement from left to right, and the black dot from right to left. So I've already added the morphisms of A to my double category. I also need to add conjoint structure, which is a fancy way of saying these corner cells for each object A in my resource theory. So they look like this, and we interpret them. For the one on the left here, I interpret this as, well, the resource is coming in along the top and then leaves along the right. So yeah, and for this one, it's coming in along the left and leaves along the bottom. And I asked that these satisfy the yanking equations, which is kind of saying that this movement has no effect on the resources themselves. Dually, I add companions. So similarly here, the resource A is coming in on the top and leaving along the left. And here it's coming in along the right and leaving along the bottom, and they must satisfy yanking equations as well. So if I do this, I construct this double category by sort of freely adding corners to my resource theory, then I have enough structure, because my resource theory is symmetric, to define crossing cells, pictured here on the left. The key insight is that the way you do it for the sort of the base case is like this, pictured up here above right. I don't really want to spend too much time on this right now, but you can sort of define them inductively by doing this and its mirror image in the two interesting cases. And that these crossing cells make my monoidal double category a monoidal double category, where the monoidal product of two cells is constructed using the crossing cells as follows. So that's pretty cool. And the crossing cells turn out to be very convenient for depicting these material histories where things can enter and leave along the left and right boundary. I guess I'm doing pretty well for time. Yes. So now in this double category I've constructed, say from my example resource theory involving kneading, baking, and eating, the cells are something like concurrent resource transformations. So here you see three cells of the double category I get when I freely add corners to that resource theory of baking bread. So here's a cell on the left, and this is a transformation of nothing into nothing, where how nothing is transformed into nothing is that we get flour in, knead it into dough, and send that back out. And then in the middle, you see a more complicated thing that transforms an oven into an oven by getting some flour in along the right, sending it out along the left, getting some dough in, baking it into bread in the oven, sending the bread out, and just keeping the oven. And then finally, along the right, we have something that transforms flour into nothing by sending the flour away, getting some bread, and then eating it. And then the point, of course, is that because I'm working in a double category, I can compose these horizontally. And when I do that, I get the overall effect of well, what if these all happened simultaneously and they exchanged things and they participated in each other's boundary exchanges. And these sort of horizontally open resource transformations are the kind of material history that our open transition systems are going to generate. And we need to take this, so this is where the technical things start. I think what's interesting about this is kind of the technical things, maybe. But, and what we're going to do to construct these transition systems that generate material history is, well, we're going to have to consider our double category as a span of reflexive graphs. You can do this for any monoidal double category. It's kind of strange. But so we're going to define Langle A Wrangle to be the graph whose vertices are objects of A, and whose edges are cells with top boundary A and bottom boundary B, for an edge from A to B, say, where we don't really care what the left and right boundary are. That's the graph that's going to be the apex of our span. And then in defining our span, well, we take the left leg, it's just going to map an edge to its sort of secret left boundary. And the right leg is going to map an edge to its secret right boundary. And in this way, we're kind of keeping track of all the structure we need to keep track of in the double category, just as a span of reflexive graphs. And now we're ready to define asituated transition systems. And it's going to be a category. So first we'll define the objects, which are asituated boundaries, which consist of a reflexive graph U, sort of like the boundary graph from before, and what I'm going to call a situation, phi U, that is just a graph morphism from U to the vertical edge monoid of exchanges, a circle bullet here, as considered as a graph. So a graph with one vertex and one edge for every element of the monoid. And so what you could think of this is, what's an asituated boundary? Well, it's a boundary where phi U assigns to each boundary event the sort of material component of that event. It tells me when that event happens, what things, if any, enter and leave the system and in what order. Right. So now an asituated transition system, this should have a domain and codomain, and the domain and codomain should be asituated boundaries u phi u and v phi v. And that's going to be a span of reflexive graphs between the sort of graph components of the situated boundaries, u and v should be here. Whoop. And along with a situation of the apex, R, and that's going to be a reflexive graph morphism from R, the sort of transition system proper, into this, this reflexive graph, the apex of our span that we sort of squished our cornering double category into. And it's required to satisfy a coherence condition, which just says, so the phi r of some transition, that tells us what the material effect of that transition is. And then it's required to satisfy this coherence condition, which says that, well, the material effect of the system, it probably has to have along its right boundary the sort of material component of the event along the right boundary. So if resources come in, it has to do something with them. And if resources go out, it has to supply those. And then dually along the left boundary. So that's the coherence condition.
5 minutes left.
Thank you, perfect. And so if you have to be a bit careful, but if you are careful, then these asituated transition systems form a planar monoidal category, by which I mean that it's not symmetric. We'll call it S of A. You can show that if A is compact closed, then S of A is also compact closed. And in particular, if you take the compact closed category of integers, then S of Z is the category accounts of systems with partita doppia, sort of double entry bookkeeping, introduced in an unpublished paper by Kattis, Sabadini, and Walters in 1998. We will try briefly to do an example. It's problematic to do examples because these are very difficult to write down, which is something for future work. But here's another Baker. We're sort of expanding our earlier Baker example. The graph in the middle is to be understood as a graph. The graphs on the left and right are to be understood as graphs, just like in our notation from before. Here on the left, the labels are intended to express the situation. So this has one non-trivial edge, and it's mapped to, well, flour enters the system by the situation. This has one non-trivial edge that is mapped to bread leaves the system by the situation. Here in the middle, the vertices are vertices, but their labels indicate what the situation of the sort of transition system itself maps them to. That's sort of like the state of the transition system from the material perspective. And so here, and yeah, similar, the transitions are labeled with the cell of the double category with corners that they're mapped to with their material effect. So this is a baker. Its state, it always has an oven, and it can also have an oven and any number of bread, where the ellipses are intended to denote that this continues infinitely. And if it has, you know, any time it can bake more bread, and the coloring indicates that when it does, well, flour must enter the system along the left. If it has bread, then it can sell bread, indicating, yeah, and the coloring indicates that bread must leave along the right boundary. And when it does this, we see sort of what happens. So when it bakes bread, well, we see that, for example, if it bakes bread and it already had 0, then the state goes from being oven to oven and bread. And this is how, with flour entering along the left boundary. Similarly, when it sells bread, well, how does it get rid of that one bread in its state? Well, it just leaves the system. And when it closes and opens, it just keeps what it has. We can also make an example. We can expand our eater. And so the eater, similarly, how you read this, the eater can either be hungry. It's sort of hungry in these top two states. And if it's hungry, it's allowed to buy bread to get more bread. And if it has bread, it can eat bread to stop being hungry. And if it's not hungry, it can digest to get hungry again. Sort of like our previous one, but taking the resources into account. And when it buys bread, that bread has to come in along the left boundary. And we haven't written the right boundary because there's nothing to write. And we see that the labels tell us that, well, when it buys, the bread just comes in and it has it. When it eats bread, it eats it. And when it digests bread, nothing happens. And so these, you know, consider, for example, that if I compose these two things, you can just imagine how that goes. And I consider the sequence of events in which, well, the baker has one bread and sells it to the eater who eats it, and then bakes one more bread and then sells that to the eater who keeps it. Well, then we could imagine, or we don't have to imagine, this is how it works. The material history generated by that sequence of events, whoops, for the baker is pictured here on the left, and for the eater is pictured here on the right. And how composition works is that the material history generated by the composite system there would be this, just the horizontal composite of the component material histories. And we could compute what happens to the resources overall. And that's kind of the big idea. That's why we needed to add these corners, and it's what I'm excited about. Thanks for listening. I'll point you to 3 papers if you're interested in more of this. So one is, of course, the paper that will appear in the proceedings of ACT called Situated Transition Systems. There was a paper at Coordination this year called The Structure of Concurrent Process Histories that dealt with this cornering construction. If you're interested in that, please check it out. And you could also look at this unpublished paper by Katis, Sabadini, and Walters called On Partita Doppia, that's sort of the inspiration for the present work. This is kind of like a generalization of that. I will stop now if you have any questions. Thanks for listening.
Question, please. You can either raise your hand or write in the chat.
There's one in the lecture hall.
Nice.
Hi, thanks for the talk. So with the sort of baking bread example, it seemed quite clear that one of the boundaries of your transition system was almost an input boundary and one was an output boundary. But if we think about the sort of gear example you gave earlier, it seems less obvious that there should be exactly 2 boundaries. So I was wondering if you could comment why, especially with the stuff at the start of the span, with having spans, why should these systems have exactly 2 boundaries?
So it's not so much that they must have exactly 2 boundaries. I mean, technically, yes, they do, but these boundaries can also be tensor products. I can take the tensor product of situated boundaries and in this way secretly have 3 boundaries, 2 of them on the right and 1 on the left, say. And you're right that these aren't inherently directed things. In my mind, due to the fact that resources must enter or leave the system and we must know which, it's sort of convenient to structure it so that they're on one side or the other, if that makes sense.
Yeah, so I guess the follow-up is, since you said you can sort of tensor these, I guess you could do everything with 1 boundary, but it just works out nicer if you have 2 separate ones. Is that, am I understanding it correctly?
Yes.
Okay.
More or less. Yeah.
Okay, we have time for another quick question. Matteo? Please.
Yes, hi. So I have 2 questions actually. The first one is this corner language related to the tile in the language of double category?
The what language of double
Myers? It's like a tile language, I think it's called, or string diagram for pro-arrow equipments.
Yeah. So it's the same thing.
There are similar corner stuff.
Mm-hmm. What we added
great.
was pro-arrow equipment structure, and indeed these are string diagrams for pro-arrow equipments.
Great. And the second is, did you think how to like relate this to the language of optics, both the graphical and the conceptual one?
So no, I haven't. If we want to sort of use this to model large-scale adaptive systems, in the world, I think that this optics sort of perception, perceptor, effector perspective is a very important ingredient in that, but I don't know how it would fit into this framework yet. That's something I'd be interested in exploring.
Cool. Okay, we are out of time, so if we can thank the speaker, if our IT wizards can unmute everyone. Okay, Mario, if you want to share your screen.
So should be.
Yep.
Can you see it right now?
We have a black thing in the middle of the screen. I guess it's a Zoom window, but aside of that, yeah. Okay, now we see. Okay, so, yes, perfect. So it is my pleasure to introduce Mario Román, that will talk about a canonical algebra of open transition systems from, again, Tallinn University of Technology, Taltech. Again, I will warn you when you have 5 minutes left, please.
Yep, thank you very much. Thank you very much, and thank you to the organizers. So this is joint work with Elena, Lavore, Alessandro, Gianola, Nicoletta, Sabadini, and Pawel, Sobocinski. And I'm going to be talking about the span graph algebra of open transition systems. So we're going to see in which sense it is canonical, and we are also going to discuss the notion of feedback in monoidal categories. So for that, I need to first introduce the algebra. So span graph is an algebra of open transition systems that was first described by Katis, Sabadini, and Walters. And the motivation, as Chad was explaining, is that many systems seem to communicate not by input-output message passing, but by synchronization over a common boundary. So if we have two gears, and one of them turns clockwise, and the other one needs to necessarily turn counterclockwise, and when one is turning counterclockwise, then the first one needs to turn clockwise. but there is no input and output. There is only the condition that the two systems need to be synchronized over the boundaries. So how can we model this situation? Well, we have two obvious choices here. A common choice for transition systems is to use a graph. The vertices of the graph will be the states of the transition systems, and then the edges will be the transitions themselves. And with this technique, we can model the two gears. Another question is how to compose them. And again, the obvious choice is to use spans, because that gives us synchronization. As Chad was explaining before, if we want to synchronize two systems, we need to have a common boundary given by yet another graph. There will be a homomorphism of graphs that maps both of them to the common boundary. Here, the homomorphism is given by these labels. And now the condition is that every time a transition fires on one of the graphs, it needs to be represented on the boundary. And also it needs to happen on the other graph, on the other system. So in this example, if a gear turns clockwise and changes the state, that gives us a B transition on the boundary, which means that the other one needs to turn counterclockwise. And conversely, on the other situation, one is turning clockwise and the other needs to be turning counterclockwise. So we can also compute explicitly the pullback, because graphs are appreciative categories. So we would get a graph for the composite system, which would have the states given by the product of the states of the two systems, and then all the valid transitions that are coherent across the boundaries. Okay, so this is just to give you an idea of how a span graph works. As you have seen, it's a compositional and a nice way of representing transition systems where synchronization happens by composition. I think that's important. And then transition systems are encoded as graphs, which feels intuitive. Finally, something that happens many times on many of the examples that we will be dealing with is that boundaries are given by single vertex graphs. So boundaries are not given by a graph with multiple states, but by a graph that has a single vertex, meaning that it doesn't have states and it's just given by a set of transitions, of valid transitions on the boundary, valid signals on the boundary. That set of signals would be the self-loops of that single vertex graph. So actually what I'm saying is that we don't use span graph. We use a full subcategory of span graph, the full subcategory of span graph on single vertex graphs. And we call this thing span graph star. Now, the problem with this category is that it may feel ad hoc. So we wanted to describe transition systems, and I justified intuitively to you why we would wanted to use graphs and why we wanted to use spans and so on. And then we need to do this particular restriction to a particular subcategory. But maybe we could want to have some more concrete mathematical justification on why this is a nice category of open transition system. In which sense this is the good category for doing transition systems. And so for that, I'm going to introduce you to a construction, which is called the state construction, and we will see how it justifies span graph. So the state construction appears many times in the literature. It has been rediscovered multiple times. It gives us a way of going from a symmetric monoidal category to the same category with some notion of memory or some notion of a state or some register that captures some information of the category. So it appears many times under different names, but the idea is always the same, is that we substitute morphisms A to B by pairs that are given by a state space, which is an object of the base category, and then by a stateful morphism, which is a morphism that goes from S times A to S times B, where this S is the state space. And these morphisms, in order for them to form a category, they need to be quotiented by an equivalence relation. So the equivalence relation is saying that we only care about the state space up to isomorphism. We have two morphisms that have different state spaces, but they are the same, just up to some isomorphism that we are putting here. Then we consider these two morphisms to be the same. That is useful when we define composition and tensoring. The definitions are the only ones that type check, so they make sense. They will put the state spaces in parallel in both cases, and they will need this condition in order to form a category, that we don't care about the state space just up to isomorphism. Okay, so now this construction is really easy, it's really naive, but it appears many times because it gives you some nice things when you apply it to reasonable categories. So for example, if you apply it to the category of sets with the Cartesian product, then you get Mealy transition systems. So you have a transition system with some state that you update and some input and some output. If you apply that to set with the coproduct, then you get something called an Elgaud transition system. If you apply to relation, you would get non-deterministic transition systems. You could apply to some distribution monad, you would get some probabilistic notion of transition system, and so on. So because this construction appears many times, it would make sense to ask what does it happen when we apply it to spans, because that should give us some notion of transition system that can synchronize. So what happens is that we will have a span that goes from S times A to S times B with the apex on E. And we can rewrite this. We can rewrite this just factoring the morphisms and saying, well, this is actually a graph here, right? Because we have some set of vertices that is given by S, the set of states, some edges that then are labeled on A and B. And if we want to use the terminal object of the category, and here you can notice that I'm only using that sets is Cartesian, then the thing we really have is a span of graphs. A span of graphs where the set of vertices is the terminal object. So I'm saying that we have single vertex graphs. And this makes a lot of sense because this is what we were waiting at the beginning. This is our span graph star algebra. And indeed, we can prove, and this is the modest contribution from our paper, is that we have a monoidal isomorphism from a state of span set to the category span graph star. The result is straightforward. The only thing you need to check is all these equivalence relations. And you are taking here spans to be a one category. So you need to identify into spans that are isomorphic. But this justifies a bit the idea of span graph star. It arises as applying the state construction over spans of sets. So we were saying, why do we use graphs and why do we do this particular restriction? This would be a category if you can think of it as some structure span category. But another way of justifying is just saying that we apply the state construction over spans. So if we want to do stateful synchronization, we want to use span graph star. And it is canonical in that sense. Okay, but this only moves the question because I have justified span graph in terms of the state construction, but you could ask me, well, why the state construction is useful. So we are going to be discussing the notion of feedback. So categories with feedback are a notion also introduced by Sabadini and Walters that is similar to traces. They give us an operator on top of a symmetric monoidal category that has the same type as traces and has some actions that make sense because they are just to say that the feedback operator behaves nicely with the monoidal structure. So let's draw them because I think that makes them clear. And the idea is that the feedback operator needs to behave nicely with compositions. It needs to behave nicely with both the unit and the tensor of the monoidal categories. It needs to behave nicely with tensoring of morphisms. And finally, we need to be able to slide isomorphisms. So notice that this is weaker than the sliding axiom for trace monoidal categories, where we allow any morphism to slide over the loop. Here we only allow this gamma when this gamma is an isomorphism to slide over the feedback loop. So then the question is, what are the differences with trace monoidal categories? The first one I was already commenting on it is that we can only slide isomorphisms instead of arbitrary morphisms. And the second difference is the failure of the Yankin axiom. So trace monoidal categories have this axiom, where if you take the trace over the swap, that should be equal to the identity. And that makes sense conceptually. You don't want to have anything between the input and the output of the loop because traces are used to compute fixed points. In categories with feedback, we don't have that. We have something between the input and the output, and we define that to be something called the delay morphism. And the idea is precisely that. With trace monoidal categories, you'll be computing the fixed point of a system. With feedback categories, you have some delay still between the input and the output. So if we compare it with other variants of traces, we are saying that feedback is weaker than trace, and balanced traces is the same thing as guarded traces in compact closed categories, and it will be guarded by this delay. And even if it's conceptually similar, it has a different type from the delay trace that we were seeing on Monday. So then why this particular set of actions? Well, I think it's interesting because we have some set of actions that still, even if it is weaker than trace categories, it still allows us to prove the following theorem. So there is a normal form theorem that says that if we write any circuit using feedback, then we can use the actions of feedback to reduce it in a unique way to a single application of feedback. So here we are using the actions of feedback and having a single feedback loop. And for that, we will need to slide the associators and unitors of the category, which are isomorphisms. The importance of this result is that it also can be used to show that state C is the free category with feedback. So we have an adjunction from symmetric monoidal categories with strong symmetric monoidal functors to categories with feedback with strong symmetric monoidal functors that also preserve the feedback operator. So the result, you can imagine how it works. We need to endow state C with a feedback structure, and the feedback operator will just take some input and some output and move them to a state space. And then the only thing we need to show is that that's the free construction, that's the free category with feedback. So if we have any other functor, it will factor uniquely through a feedback preserving functor from the state construction. So you can imagine how all of this works. And so we have justified then the state construction in terms of these categories with feedback. And we can reread our result and say that span graph star is the free category with feedback over span set. So if we want to put something over span set that has feedback, understood in this really weak way, we need to go through span graph star. So I think this is an interesting justification, because at the beginning I was justifying to use span graph in terms of we usually draw graphs when we do transition systems. We want to use spans for synchronization, but now we have some mathematical compact justification. And why do we use transition graphs to draw transition systems? Well, there is a really obvious inclusion of sets into span, a functor that takes any morphism and puts it at the right leg of the span. That lives by the state construction, which is functorial, to an inclusion of Mealy transition systems into span graph star, which is the thing that we are really doing when we draw the transition system as a graph, draw any transition system as a graph. Okay, so now I have justified to you that this state construction is useful, that it justifies the previous span graph star construction, and that it can be used to give some notions of feedback. So now the next step is to try to generalize this state construction. And for that, I'm going to go to the talk I gave last year at ACT, where we were describing how to read flows of information using the monoidal bicategory of profunctors. So we had some notion of normal flow, where things go from input to output, and some flow. And now we can have some flow with feedback, where we take some input, we take some input from the feedback loop, then we produce an output and an output for the feedback loop. So these are just drawings that express some flow of information. And what I think is interesting, I'm not going to recall all the details, but what I think is interesting is that if we read these things on the monoidal bicategory of profunctors, then we will get profunctors that represent the home profunctor and the state construction respectively. So these define monads on the bicategory of profunctors. The one on the left is just the home profunctor, which gives you morphisms, normal morphisms from input to output. The one on the right is the state construction. So we have here this S times I to S times O, and then we have some coends. So coends are particular kinds of colimits that appear when we compose profunctors. And in this case, the coend is giving us a way of expressing the quotient relation that we were getting on top of the state construction. Because monads on the bicategory of profunctors correspond to a new assignment of morphism to a category, they correspond to an identity and objects functor. This is just like putting new morphisms on top of our previous category. And this is the thing we were doing on the state construction. So I'm going to go back. And the thing we were doing on the state construction, state construction here is that we were substituting basically the set of morphisms from A to B to a set of pairs, where we have the state space and a stateful morphism. So this is the new set of morphisms, but we have the same category. So this is the same as to say that we have an identity and objects functor from C to a state of C. So we have a monad on the bicategory of profunctors on top of C. Now, this I think is nice in that it justifies also the state construction from another point of view. If we draw a loop with feedback, then that will give us in profunctors the formula for the state construction. But the second thing we can do with this is to generalize the state construction. So we can try to get not the most general form of feedback, but some nice generalization of feedback. And this will be given by taking the coend over a different category that we were taking before. This is interesting because we are going to be seeing the free constructions for many variants of the actions of feedback. So we choose one variant of the actions that was these categories with feedback, but there are many others. And we can get the same construction for all of them. So we can generalize the state construction and just say that this is the free construction for all these categories.
5 minutes left.
Thank you. So for example, if we have we want to have trace categories without janking, then what we need to do is to take the coend over the category C. And then the formula would be exactly the state construction with the janking, without the janking action, but with the sliding action that we have for trace monoidal categories. If we want to recover the categories with feedback of Sabadini and Walters, and we want to recover the previous state construction, what we need to do is to take the coend not over C, but over the core of C. And the core of C is the subgroupoid of isomorphisms. So we restrict C only to its isomorphisms, and then we have this quotient in relation only on isomorphisms, as we were doing before. If we want to have some categories with some initialized state that then changes every time we apply a sliding axiom, then we can do so by using some comma categories, some slice categories, sorry. And if we want to have some form of delayed traces, we can do so by putting some functor on one side. And we can do so if the functor is stromonoidal, because then applying the functor and tensoring will be giving us a stromonoidal action, which is the thing we need to put here in order to have some notion of feedback. So this is to say that if you have any other variant of categories with feedback, we can still apply variants of the state construction, and they work the same, and the normal form holds the same way. So the proof is basically the same. So we can capture all those slightly different axiomatizations with the state construction. So the free SAS things will be given by the state construction. So as a conclusion, we have shown that span graph start is state of span set, which is interesting because we had this algebra of open transition system that was given by graphs, and where we had to do this particular restriction to a full subcategory. But now we can justify it just by saying that this is the free way of adding feedback to the category spans. This is interesting because it also makes many results from the literature easier. So you can do the same thing if you have spans, you can do the same thing with co-spans. And there are some results on the literature, both on span set and co-span set, that become really easy if you have this characterization. So this was previously not known, and the thing it's doing is simplifying many other proofs. So there are some proofs that describe these categories of span graph, star, and co-span graph as categories with other generators. You can get that for free if you're using this characterization of state span set. So the state construction appears many, many times across the literature. It has been rediscovered and reinvented many times. So I think that was why it was really interesting to put this together with all the rest of the things we are telling here. So why do we want to express span in terms of this construction? Is because the construction appears many times. And we can characterize it as the free category with feedback, which also allows you to not have to reinvent it again, but just say, I'm going to take the free category with feedback or some variant of feedback if I need some variant of this state construction. And then categories with feedback are a weakening of traces, but they still satisfy this normal form theorem. And for any other, don't satisfy the Yankin axiom, but for any other variant of feedback that doesn't satisfy necessarily the Yankin axiom, but does satisfy this some weakening of traces with some sliding axiom, we can do the same construction. So state can be generalized to other variants of feedback. And finally, something that is still missing here, and I think will be really interesting, would be to relate this approach of transition systems. Now that we know in which sense it is canonical or is can be mathematically justified, to relate it to the most common approach of using coalgebras for transition systems. That can be done via Profunctors, but we haven't yet published anything on that regard. So we are studying that part. I think that's all. Thank you very much.
Thank you. So we have a couple of minutes for questions.
A question from Cole.
Nice.
In the case when you're working over a closed monodal category, is this state construction the same as like taking the Kleisli category of a state monad, or is it totally different?
No, I think no, it's different because the state monad would give you a single state that every morphism has. So the type of the morphisms is the same, but then the state, so here, for example, the state monad would have a fixed S here. Whereas here we are allowing every morphism to have a different S. So the Kleisli category of the state monad will have a fixed state set, I guess. And then it would be not changing from one morphism to the other. So I can have two different morphisms on this category and they can have different state spaces. Whereas I guess with this state monad, you need to have a single state space for all the morphisms on the category. Does that make sense?
Yeah.
Thank you.
Another question from Matteo.
Great.
Hi, Mario. Very nice talk. And my question is, can you recover, like in the Sprunger-Katsumata paper,
the stateful morphisms are actually like time dependent. So each like iteration of this feedback loop can actually use a different, let's say, function to happen. Can you do this in this framework, like especially with the latest slide where you described delay traces in terms of this koan construction?
So I don't actually know, because I remember they do this indexing. So I guess if you have multiple morphisms indexed by natural numbers, then you could show that that's a category with feedback. I would not know if that's the free category with feedback for some variant of the axioms of feedback. I don't know. I'm almost sure you can show that their construction is a category with feedback. And in fact, on their paper, they have the same construction over a different name.
Yes, yes.
But when they index by the natural numbers, I am sure you can show that's a category with feedback still. I'm not sure if you can exhibit this as the free something, as the free state, as the state construction over some other monoidal action.
All right. I see. Thank you very much.
Taking like, instead of sets, you could take like sets in the natural numbers and try to do something there, but I'm not sure. Yeah, that's a good question.
It might be that that's sufficient and you take diamond to be the shift.
Sufficient you take the diamond to the shift. Yeah, it may be. But I think their construction is slightly different. So I have another paper that is called infinite cones, feedback via infinite cones, I think, something like this, where they use this.
Guys, I'm sorry, maybe this can be deferred to a breakout room discussion.
Yeah, thank you.
Please, let's unmute everyone and thank the speaker. Okay, Joe.
Yes.
If you want to share your screen.
Great. Okay, is that working?
Yes, it's working perfectly. So now I'll introduce a speaker, Joe Moeller from UC Riverside, that will talk about non-commutative network models. As usual, warning when you have 5 minutes left.
Okay, so yeah, I'm talking about non-commutative network models, which is a paper from my thesis that I don't feel like I get to talk about very much, so I'm excited to talk about it. Usually I have to talk about just network models, so yeah, first I want to, I did this work while I was at UC Riverside, and now I'm at NIST. That's the reason for the 2 institutions here. And here's a picture of a goose and a turtle in case this slide is too boring. But here's the paper that I'm talking about, and here's just an outline of what I'll tell you. First, I'll tell you about network models, but only really quickly so that you can follow the rest of the talk, and then I'll tell you about the Ekman-Hilton argument, a variant of it for network models, and how Knaser graphs and graph products of monoids will help us construct free undirected network models. Okay, so let's do that. So before network models, I'll tell you about species, just in case you don't know about these. And before that, I have to tell you that a symmetric groupoid is the category of these particular finite sets. You could just take the category, you could just take the objects to be any finite sets, but it's a skeleton if you take these particular ones with bijections between them. So all of those morphisms are going to be automorphisms, and it just looks like the symmetric groups thought of as one object categories, and you take the coproduct of all those. And so Joyal defined a combinatorial species to be a functor from this symmetric groupoid into the category of sets. And the purpose of calling it a combinatorial species is that it's one of these things describes a type of sort of combinatorial gizmo that has some finite number of nodes, and permuting those nodes defines an action on the set of gizmos with n nodes. So the example that's going to be relevant here is simple graphs. So graphs with no loops, at most one edge between a pair of nodes and no direction. So here's 3 of them. as an example. And so the functor would send the finite set with n elements to the set of graphs with n nodes. So what's a network model? A network model is like a species, except that it's a lax symmetric monoidal functor from the symmetric groupoid into the category of monoids. And so what does that extra structure look like? The monoid structure on each of these monoids f of n, we think of it as an overlay operation. So here's two graphs with 4 nodes, and then this monoid operation cup is telling us how to take them and combine them and get a new graph with 4 nodes. And then the laxator for the lax monoidal structure tells us how to take a graph on 3 and then a graph on 4 and turn that into a graph on 7 nodes. So these are very natural things you'd want to do with graphs or anything that's sort of like a graph. So this is what I take to be the basic combinatorial ingredients of a thing that I want to think of as being enough like a graph that it fits into this framework. And here's a bunch of examples. So simple graphs, like I said, but you could imagine, just drawing directions on these edges or having multiple edges. You can color the edges different colors if you allow multiple, and so overlaying them just puts like a red and a blue next to each other. Hypergraphs, Petri nets, anything that's sort of like a graph, but not completely anything, because acyclic graphs is a good non-example. So you could imagine that if I said these were supposed to be acyclic graphs, and I attempt to overlay these two, these are acyclic, but then suddenly a cycle appears. So that doesn't work out. So that's network models. What do we do with network models? The intention behind the definition is to end up constructing an operad of networks. And the way that you do that is you first apply the symmetric monoidal growth and deconstruction. That gives you a symmetric monoidal category. And then with a symmetric monoidal category, you can take the underlying operad. And so it gives an operad that looks sort of like this. But this is just for the sake of telling you what network models are for. I'm not actually going to be talking about the operad very much today. I just wanted to give you the background on what network models are and what we do with them. So let me talk about constructing network models. So first I'll tell you one way to construct network models, and then it's going to lead to, I think, an algebraic problem, which this paper is mainly addressing, and it has a solution that I think of as a combinatorial solution. So it's a combinatorial solution to an algebraic problem that arose in studying network models. So here's a construction for a network model given a monoid. So if you have this monoid M, then you can turn it into a network model by saying, take the number n and assign it to the monoid of the product of M with itself, n choose 2 times. And so the way you're supposed to think of that is that we're giving a copy of M for every possible pair of nodes that you would want to put something between. So for instance, if we use the Boolean monoid with plus, so 0, 1, and 1 plus 1 is 1, then you get simple graphs back. So you have, let's say, 4 nodes, there's 6 possible pairs, and you can either put 0 between them, and that means don't put an edge, or you put 1 between them, and it means there is an edge, and when you overlay them, an edge and an edge just becomes an edge. Similar to that, but different enough, is natural numbers with addition, and that will look like network model, will look like graphs that have multiple edges between a pair of nodes, but a natural number of them, and you can't distinguish between them. So if you have 3 and 4, and you try to overlay those, you just get 7. And then a slight variation of that is that you can take some set and then you take the power set of that with union. And the result is that you have edges which are labeled by elements of this set. And overlaying them is taking the union of those sets, of those subsets. But there's a relation in this construction. So it seems like a lot of examples of network models could come out of this construction, but there's a relation that's being automatically imposed here. Elements of the monoids that you're constructing that correspond to disjoint pieces of the graph are automatically commuting with each other. So like, here's the relation as a, sort of as an impressionistic picture of it, but it's really obvious if you look at it as a product, as like a set of tuples, that these things that correspond to disjoint pieces are automatically going to commute with each other. And so if you wanted to create a network model that didn't have this, like if you were trying to construct network models freely, then this isn't going to work for that. So that's a large class of examples that are not being constructed here. So maybe instead we can say, let's take the coproduct of these monoids the correct number of times. And this isn't going to work out, as we'll see in a sec, but why would you want this? Because when you take a coproduct of monoids, the elements of the resulting monoid is like a list, and so the elements that are coming from the different components of that coproduct are not going to commute with each other. So that seems like a way to solve this, to get rid of this commutativity that you weren't asking for. But it's not going to work out because components of your monoid for a network model that correspond to disjoint pieces in the graph are necessarily going to commute with each other. And so this is the Ekman-Hilton argument for network models. So here's the thing that sort of looks like the usual Ekman-Hilton argument, but here it is in a sort of picture language for simple graphs in this case, and you can imagine what it is really saying for general network models. But if you have this 3-node component and this 4-node component that you are talking about putting inside of a graph, then these are 2 disjoint pieces, but you could represent them as taking this piece and overlaying it with an empty graph, and an empty graph and overlaying that with this piece and taking their disjoint union. But everything commutes with a unit in a monoid automatically, and then we can apply the middle four interchange law again and get the reverse of the thing that we started with. So when things are disjoint, they have to commute with each other. So we don't have the freedom to make everything not commute with each other. So what we want to do is have we want to take a coproduct of the right number of monoids, copies of this monoid, and then impose some kind of commutativity relation specifically for components that are disjoint from each other. So let's try to describe that now. This is the first few examples. So if we're assigned, what do we assign 1 to? It's the empty coproduct, and then 1 also gets assigned to the empty coproduct because there are no distinct pairs in a set with 1 element. But in 2, we finally get a distinct pair, and so we put the monoid M as a set of possible edges between 2 nodes. This is looking easy so far. The next one is 3, and we in the case of 3 nodes, we have 3 edges, but none of them are disjoint from each other. So we don't have to impose any commutativity relations. This is not looking too bad so far. But then with 4, we have 6 pairs of nodes, and so we have 6 copies of the monoid, and 3 pairs of edges are disjoint, and so we have these 3 relations. It might be hard to see the commas between the relations, but there's 3 relations here. Fine. Then for 5, we have 10 copies of the monoid and 15 relations between them. And this is getting unruly, so maybe it would be nice to think like a combinatorialist or something. And so let's do that. I got rid of the first 2 examples because they're too easy. But we can see now that, here's what I was describing. We have a graph with 3 nodes, and there's 3 not disjoint edges between them. And so in the red picture, I'll be drawing nodes for the edges over here, and I'll draw an edge between them when they are disjoint. And so in this case, none of them are disjoint, and so we get this graph here, and that corresponds to saying that there are no relations here. But then in 4, in the 4 case, we had 6. Sorry, I drew 6 here, but I meant 3. We had 3 relations here, and that corresponds to the 3 edges that you get in this graph that is describing the disjointness of the edges in this complete graph on 4. And in the 5 case, we get 15, and it's coming from the 15 disjoint pairs of edges in the complete graph on 5. And that gives you this graph. And this sequence of graphs is a famous sequence of graphs. They're called the Knaser graphs. Just realized I didn't write that anywhere. The name of these graphs are the Knaser graphs, specifically indexed by n and 2, if you know what that means. So this is something that we can use to describe this disjointness relation that we're trying to impose on these coproducts of monoids. This is what we're going to use, but how do you use a graph to impose relations on a monoid, to describe a mixture of products and coproducts?
5 minutes left.
Great. A graph product, this is a graph product of monoids. So don't confuse it with some kind of thing that you do to graphs. It's a thing that you do to monoids, but it's described by a graph. It was invented by Green in 1990, and it describes exactly what we need here. If you have a graph and you have a bunch of monoids corresponding to each of the nodes, then you can construct this monoid, which takes the it looks like a coproduct when there's no edge connecting two monoids, and it looks like a product when there's an edge connecting them. And so here's like the way that they wrote it down originally, but here's a categorical description of it. So if you have this graph, here, construct this category. There's no way to compose edges here that would give you any non-trivial paths, and so this is a category basically as it's drawn. And then now take this diagram based on the monoids. This is a diagram in the category of monoids, based on the monoids that you put on each of these nodes. You're putting this product in between them, and then these maps are the inclusion maps. You get inclusion maps into a product in the category of monoids. And if you take this diagram and you take its co-limit, then you get precisely this graph product of monoids. And this is exactly all of the ingredients that we need to describe the network model that has the fewest relations. And so this is it. We define a network model for a given monoid, which sends n to the n2 Knaser graph of that monoid, and this theorem is saying that really is the free network model on that monoid with the caveat that we're only talking here about network models that describe networks which are undirected. So there's a trivial involution. So switching two nodes doesn't change the value that you assigned to that pair of nodes. But we have a left adjoint. This construction describes the left adjoint to something, and so it really is free on the given monoid. And that's the end of my talk. So here's some references.
Thank you very much. Are there any questions? Let me see in the chat. Okay, I have a question. I don't know how pertinent it is, but basically, if I understood correctly, one of the things that a non-commutative network model allows you to do is to keep track of when you add the order in which basically edges in a node, for instance, in a graph are presented, right?
Yes.
Have you thought about using this to define some kind of dynamics on these graphs? Like if I have my network and at some point I want to move it in some way, have you thought about ways to do this or any ideas?
No, but it sounds really cool.
Cool. Okay.
There's a question here, if we can take it.
Please.
Yeah, so this is just a technical question, so I don't understand this too much, but from the construction that you made, it seems a little bit like you're doing a left-con extension of some sort, and that's why you're getting this freeness. So it's looking like there's like a general picture of what you're doing. So it's just maybe a comment rather than a question. Yeah, that's all.
Thanks. I'll think about it.
Hans, if you have a quick question.
Yes. Are you able to give us just a very high-level description of how this monoidal growth and deconstruction works?
Yeah. So maybe I'll use my whiteboard right behind me.
May I suggest that maybe this is a better question for a breakout room, since Joe wrote a rather big paper about the monoidal growth and deconstruction. I don't know.
Yeah.
Maybe
okay.
I can just read the abstract of the paper then. My apologies.
No, it's fine. Discussion is incentivized, but we are basically right on time right now. So,
yeah.
Okay. Thank you very much. Let's unmute and thank the speaker. Thank you. Okay, Gunnar, if you want to share your screen. Great. Okay, so it is my pleasure to introduce Gunnar Fløystad. I hope I pronounce it correctly, from University of Bergen, that will talk about profunctors between posets and preserving cuts. Please,
yeah, thank you.
As usual, warning when you have 5 minutes left.
Thank you. And thank you for the chance to speak here at this very nice conference. So my background is commutative algebra, more with a combinatorial flavor. I recently read the 7 Sketches book by Fong and Spivak and was quite taken by that. And I see that profunctors relate well to things I have been working on. So let me give an overview here. So I'll start by recalling notions concerning posets and profunctors. And then I'll give a running example in my presentation here. And then I can come to the main statement. And lastly, I will give some applications. So we start with poset, and I guess most of you will be quite familiar with the next few slides here. So I have a Hasse diagram of the posets. A is less than B. Say B and C are not comparable. And if I have my poset, I can take a cut in the poset, so I can divide it into an upper part, which will be called a poset filter, and a lower part called a poset ideal. So the cut is this pair I and its complementary set F, which is the filter. And a distributive lattice is then all the cuts of P, and this is ordered by inclusion on the poset ideals. So then we have the morphisms between posets, the order preserving maps. That gives me the homomorphisms here. Sorry. And this is an internal hom. Posets form a Cartesian closed category. And now the distributive lattice can be identified with the order preserving maps from the opposite poset to the Boolean poset with two elements. So here you would take a cut and map everything down here to 1 and everything up here to 0. That will give you an element here. The distributive lattice has a distinguished top element and a bottom element, and I will call the top element by the infinity symbol. So if I have a set here considered as a discrete poset, then the distributive lattice will be simply all the subsets, identifies as all the subsets of A. It's a Boolean poset on A. If I have a chain here, then the distributive lattice, which consists of all the cuts in the chain, well, there will be n+1 cuts. And they will again form a chain. So so n hat here identifies as the chain of n+1 element, and the top element, infinity, is n+1. So now come the notion of profunctor, which I define here as an order preserving map from P to the distributive lattice. And you see here that via well, here you have the the Cartesian closed structure of posets and uncurry here, and you see that a profunctor corresponds to a cut in this poset here. So normally, I guess profunctors will be defined using to be an element here. So profunctors corresponds to cuts in this P up times Q, the product poset here. So this is maybe a slight digression here. So if I have sets, then a profunctor from A to B is a relation between A and B. So posets. So in general, of course, you can have profunctors between categories. The profunctors between posets are really, you consider posets as Boolean rich categories, but in ordinary categories, a profunctor would be a functor from C to the presheaves on D. Okay, so let me come now to the running example. So I look at a profunctor from the 6th chain to the 4th chain. That is the same as order preserving map from the 6th chain to the distributive lattice on the 4th chain, which is just the 4th chain union infinity. And moreover, it's also the same as a cut in this product poset here. So if I have a profunctor, then I can, sorry. Yeah, so if I have a profunctor, I can define its graph. Here I have my running example where I have this 6-element chain here, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, the rows here, and lastly, the top element, infinity here. And you see this is the profunctor which says sends 5 to 4 here. That's why I plot the red circle here. And 6 is sent to infinity. And infinities I don't plot in the graph. Only the sort of the finite parts here of the poset are plotted for the graph. Then I can complete this figure here by to a snake here going like this. So I put in the blue dots here, and the blue dots here will be called the ascent of the profunctor. And either the graph determines the profunctor or the ascent determines the profunctor. If I take the union of the graph union the ascent, I get what I call the boundary of the cut. So the cut corresponding to this profunctor here. So I'm moving the cursor now, and you'll see the cut. It goes like that between the red and the blue dots. And sort of the blue dots are somehow on the top of the poset filter corresponding to the cut. This is in the when considering the cut here. This is the smallest element in the product, and this here is the largest element in the product. Okay, so let's. What is a profunctor? What do I mean? I take a general profunctor. What do I mean by the graph and ascent for a profunctor from P to Q? P and Q are general posets. So profunctor here sends an element P to a cut in Q. So it's a poset ideal here, and it's complementary filter. And let UP denote the underlying set of the poset. Then the graph of the profunctor will be, I let a little p run through the poset and take all pairs p comma q, where q is minimal in the filter here. And the ascent will consist of all p q such that q is in the poset ideal f of p, but q is not in f of p prime for any p prime less than p. And these are subsets of this product set here. And the union can be called the boundary of this cut defined by f. Okay, so the ascent here will be a map sending a profunctor from P to Q to an element here. So this here is, so UP up times UQ is then a set, and putting the hat here makes it the Boolean poset on this set here. So f is sent to lambda f, and the bar here just I omit the. So really here is of course the complement of lambda f. It should be written here, but I just omit it here. And so it sends a profunctor f to the ascent. Now the gamma map does almost the same here concerning the graph, but I put the graph on this side here. That means that here on the first place, there's really gamma f complement. So usually you think of the first element here as the element of the Boolean poset. So it's really sending f here to lambda f, and here it sends f to the complement of gamma f, if you think of the first factor here as the elements of the Boolean posets. Okay, so now I'm going to lift these two maps here to a higher level. So I'm starting taking a cut for the profunctors from P to Q. So I is a set of profunctor closed undertaking smaller profunctors. And then I define the map, this map here. And so this object here are the cuts. The elements here are the cuts for this set of profunctors. The elements here, what are these? Well, if I had only one hat here, then it would be the Boolean poset on this product here. When I have two hats, the elements here are cuts in the Boolean posets. So I will take a cut here, well, a cut here, that's an element here, and move and map it to a cut in the Boolean poset. And this cut here is mapped to the following cut. So I take that f, little f, vary in script f, and I form the ascents here. And that gives me element in the Boolean poset on the product. And I take the poset filter generated by all these ascents. And similarly, I have the lifting of the gamma map. Then I map this cut here to the following cut, where I form, take all these elements here, letting f vary in script I. And I take, this gives me elements in the Boolean poset, and I take the poset ideal generated by all these elements in the Boolean poset of UP up times UQ. That will give me the poset ideal and therefore a cut in the Boolean poset. That's an element here. Okay, now I come to the main statement here. And the statement says that if I comma f is a cut for the profunctors, then this pair here is a cut for the Boolean poset on UP up times UQ. That means, that says simply that these two maps here are precisely the same map. Because here the filter will be this, and here the filters are these things here. And in fact, together they form a cut. In order for this to actually hold, you can't do that for arbitrary posets, because you have to be able to, the graph and the ascent has to sort of remember which profunctor it comes from. So you have to have the notion of well-founded poset, which means that well, a poset P is well-founded if every subset of P has a minimal element. It's equivalent to every descending chain in the poset stabilizing. And it's then the descending chain in the poset is essentially finite. Okay, so this latter Boolean poset here, of course, can be written in this way here. So really, you are taking a cut here in these profunctors here, and then you're getting a cut here in the profunctors from these, between these two sets, or simply a relation between these two sets, really. Okay, let me illustrate the theorem here with the running example. So I look at the profunctors from the 6th chain to the 4th chain, and I take a cut there. So then for the filter, I take the ascents of elements in the filter, and I take graphs of elements in the ideal. Then the theorem in this case here would say the following: if you take any subsets of this product set, yeah, so really I should maybe have U in front of there, because there is no order on this set now. I just take any subset S. Then this any subset here would either contain a blue path from script F, or the complement will contain a red path from script I.
5 minutes left.
Thank you. These two cases are mutually exclusive. So either the first statement is true, or the second statement is true, not true at the same time. Okay, now I come sort of to my disappointment with the statement, and that is, of course, you have the natural inclusions here. This where you forget this is just a set structure. You forget the order relations, and what we do is getting from a cut for this the profunctors from P to Q to cut to this profunctors from UP to UQ, and so you have this map here, and of course you would like that this map here is functorial in the posets P and Q. So for instance, you would like, if you take UP to P and take the identity from Q to Q here, you would get down here and then get further down here. That would be the case if this correspondent had functoriality properties, but I have not, but there does not seem to be any good way to factor this map down here so that the composition actually gives you the cut over here. And so that is somehow the main thing which I say I'm happy about, and which I really would like to understand better with this result. Okay, let me just come to, I only got a couple of minutes left, so let me just give the applications. So what we get in this theorem is cuts here, and this here is Boolean posets. And with cuts in Boolean posets, you can do quite a number of things. So here's an example of a cut in a Boolean poset. If you look at the maximal elements, say 1, 2, and 2, 3, they give you a graph here. And in general, cuts in Boolean posets, they correspond to precisely to simplicial complexes. And then you have topology, you have combinatorics, and you have you can also form rings, standard reasoning rings, and do a lot of algebra. So you have a lot to play with when you have cuts in Boolean posets. And here's the first nice thing. When Q is a chain, so Q hat will be a chain on n plus 1 element. Then if I take a cut here and get the corresponding cut here in the Boolean poset, then this cut here will give a simplicial complex. And what kind of simplicial complexes does it give? Well, the nice thing is that the corresponding simplicial complex is a triangulated ball. And moreover, its boundary will be a simplicial sphere, which has a very nice description. So in fact, so this gives you a machine to construct enormous amounts of simplicial spheres, because you're free to choose any poset P to any number n, and free to choose any cut there, and you will get actually a simplicial sphere. So this generalizes some previous results here. And lastly, an application to ideals in polynomial rings. So I'm looking at the profunctors from the natural numbers to the natural numbers. And this may be given a suitable topology. And if I have a open poset ideal I there, they correspond one-to-one to a certain class of ideals in infinite dimensional polynomial rings, strongly stable ideals. You probably don't know what a strongly stable ideal, but just let me briefly give the intuition. And that is, if you have ideals in polynomial rings, you may ask, what are the most degenerate ideals you possibly can have in a polynomial ring? And those most degenerate ideals are precisely the strongly stable ideals. So they are quite distinguished in polynomial rings. Yeah. Okay, so let me just here end with the thing I would like to understand. And that is the end of the talk. Thank you.
Thank you very much. Are there any questions? Yeah, Nicholas, please.
Thank you very much for this nice talk. And I was just wondering, because I've recently worked a lot with Jochen Koch in these decomposition spaces. I mean, if you can put one cut on a poset, it sort of almost cries out for putting a number of cuts on the poset. And I was wondering, is there are there any meaningful operations, for example, then for getting again this cut? Or because I have a feeling it could be giving rise to decomposition space, where then one of the face maps could maybe implement profunctor composition. So have you thought about this?
No. I'm afraid not. So I'm fairly new to much of the material here. So, but yeah, I noted that you talked about decomposition spaces, and Joachim Koch is very interested in this. So yeah, I would like to learn more about that.
Maybe we could talk more offline. Yeah, thanks.
So I have a question myself, maybe a bit of a naive one, but given that you work with posets, and posets are a particular case of categories, how much of all these already categorical kind of setup can be generalized from posets to, for instance, categories? I don't know if that's even possible.
Yeah, that is an interesting question, and that's something I really want to think about and understand. So the thing is that the two significant notions here are the graph and the ascent. And they are, as I define it, they very much are sort of they are defined by the underlying set structure. Mm-hmm. And that may be one of the reasons why I find this map here is hard to make functorial. So yeah, so if this could probably the graph and ascent could be understood in some better way, not just using the set-like definitions, that might give some a path to look into. Yeah.
Mm-hmm. Okay, thank you. Hans?
Just a comment, I would say, just to piggyback on what Fab said, is that, I mean, one, maybe a simpler generalization is to consider categories enriched, in monoids other than the Boolean. So maybe simple monoids like the unit interval with, times and 1, for example.
Yeah, that's a good idea to think about. Yes, yeah. Well, thank you.
Well, thank you very much. Let's unmute ourselves and thank the speaker. Okay, everyone. So I think that's it for this session. And now we have an hour-long break. Go for lunch if your time zone allows.